Chapter 8.4 is going to be dealing with the determinants of matrices. What you're going to have to walk away with is being able to calculate the determinant of a 2 by 2 matrix and a 3 by 3 matrix. All other matrices you would just be able to use the calculator. This other goal is directly taken from the Iowa core. This is going to be that knowing the determinant of a square matrix is non-zero if and only if the matrix has a multiplicative inverse. So this goes both ways. If there's a multiplicative inverse, then the determinant is non-zero. So it's not zero, basically, is what that's saying. And this could be very helpful because what we found out is that the multiplicative inverse of matrices was not division like you might think the inverse of multiplication would be. We found that we actually don't have division with matrices, so this is where we would have to call upon A inverse if we were trying to do something like solve for B in this situation. We would have to multiply A. We wouldn't be able to divide by A, but what we would be able to do is multiply by A inverse, and these would undo each other, and we would just get the identity matrix, and therefore get B by itself. So the idea was to calculate for A inverse if you had something like A equals and then 1, 1, 2, 4, something like that. The idea is if you wanted to find the inverse of that, it was kind of a long process. You would have to take that matrix that you were trying to find the inverse of, put it up against an identity matrix of the same dimension, and do the row operations to get this into the identity matrix, and then this one would transform into your A inverse along the way as you operated on this. So you could see how this could be a very long process, and if you could save yourself some time by, if when you calculated the determinant of that square matrix and it was equal to 0, you wouldn't even have to do all that because you would know it didn't exist. So, with that being said, our first goal is to calculate the determinant of a 2 by 2. And the determinant definition is going to really be defined by this operation down here. So one thing to kind of pull to your attention, or something that you probably noticed, is instead of having the entries labeled A1, 1 and then A1, 2 for being in row 1, column 2, we're going to instead just name columns a different letter. And this kind of helps in the definition that you'll see down here. So just so you know, this is going to be kind of a new notation for what we're talking about here. So if we were given this matrix A, and it's a 2 by 2, you can see, and I wanted to find the determinant of it. So here's one notation, here's another notation. The more standard notation of determinant are the absolute value bars, or these determinant bars right here. So notation, kind of know what that means when we're talking matrices. When we look at the absolute value bars, we're just trying to find the determinant. So here, I'm trying to find the determinant of this 2 by 2. What we will really be doing is just taking the cross products, multiplying those, and then subtracting the cross products here. So A sub 2 times B sub 1 is going to be that second portion. Alright, so an example of this is, here's my 2 by 2. What the directions are saying is find the determinant of A. That's our notation. So if I were to do that, then the determinant of A is equal to 2 times 2 minus negative 3 times 1. And when you simplify that, we're going to get 7. So our determinant of this particular 2 by 2 is 7. Alright, so that was one of our objectives, being able to calculate the determinant of a 2 by 2. Not so bad, right? And then an application of the determinant here is that, once again, as mentioned in our objectives, that if you get something other than 0, then we know that there is going to be a multiplicative inverse that we could calculate. So in this particular case, we said that the determinant of A was equal to 7, so therefore, yes, we can calculate an inverse. So we can calculate A inverse. And I'm not going to do all of it, but what I am just going to say is that if we were to start that process, I would take 2, negative 3, 1, 2, and I would put that up against the same dimension identity matrix. And what I would have to do are the row operations. So in this case, I would probably take row 1 and switch it with row 2. And then what I would have is a 1 up in the corner, and I would proceed to empty out column 1 of all of its values underneath this one. and then I would get a diagonal of 1s, and then I would turn it around and empty out everything up here. So we would get that diagonal of 1s and all 0s over here and transform this side. When we would do that, I'm going to just kind of show you what we would have gotten had we done those operations. We would have gotten this. So this would be our matrix A inverse, and again we would have had to go through that long process of finding it, but it was nice to know that hey, we would have some sort of nice end. Alright, let's look at this one. If I wanted to find the determinant of B here, what I would go ahead and do is take 2 times 4 minus 4 times 2, and you can see this one is equal to 0. So what I want you to consider is that this system right here would be 2x equals 2. Remember when we had our augmented matrices like that, and then we could set up a system, and then we have 4x equals 4, so if we were to look at it like this. So one thing to consider then is these are the same exact line. And just think about all of those things that we discussed about solving systems of equations when they're the same exact lines. What kind of things would happen if we were trying to solve a system in which those equations were actually the same? So I just want to show you that if we did set this up and we began to try to find that inverse matrix, what would happen is you would start to say, hey, I could easily get rid of this by taking row 1 times negative 2 and then adding it to row 2 to get a new row 2. And in that process, what would end up happening is you're going to be wiping out all of this stuff at the beginning. So 0, 1, so we're going to get 0, 0, those wiped out, and then negative 2, 1. So in the end, you're going to have 2, 2, 1, 0, and then 0, 0, negative 2, 1. And at this point, you would realize, hey, there's nothing I can do beyond this that I could achieve a diagonal of 1s and then 0s. Okay, so just kind of think of the implications of these matrices in which we wouldn't be able to find an inverse. Alright, so those were 2 of our objectives that we were talking about. Now we're also going to have to meet the objective of being able to find the determinant of a 3 by 3. So here is kind of a definition or kind of a process for how we're going to go about finding the determinant of a 3 by 3, but really doing the example fully through is what's going to help. So I try to start you off with this right here, so go ahead and read through that, but I'm going to just do it down here. So the very first thing is we need to calculate minors, and the minors actually are going to be looking at, we're going to have 9 different minors because there's a 3 by 3 matrix here, and this first minor is going to be looking at row 1 and column 1 and wiping them actually out of your original matrix. So row 1 and column 1 are actually going to be wiped out. Then what will be left for M11 would just be 2, 5, negative 6, and 4. Those were the values that are left, and we're going to take the determinant of that 2 by 2 that we have left. So we would have 2 times 4, which is 8, minus negative 6 times 50 would be negative 30. So we're going to get 38 is our minor in row 1, column 1. Alright, this second minor entry, so minor 1, 2, would be doing, I'm going to change marker color here. So for this one, we would be looking at row 1 being eliminated, so this one's still gone, but this time column 2 is going to be gone. So that leaves 3, 5, 4, 4. So we're going to have 3, 5, 4, 4, and when we do the determinant of that 2 by 2, we're going to get 3 times 4, which is 12, minus 5 times 4, which is 20, and then we're going to get negative 8 for that entry right there. M13, we're going to be looking at row 1 gone and then column 3 gone. So what we're going to have for minor 1, 3 is this determinant right here. So we're going to have 3 times negative 6, which is negative 18, minus 2 times 4, which is 8, so we're going to get negative 26. I'll do one more, erase these so we don't get our lines confused. Alright, we're going to go ahead and do M21. So now we are in row 2, so 2, 1. We're going to take out row 2 and column 1. And what we're going to be looking then at is negative 1, 0, negative 6, 4. So when we go ahead and do that, we're going to get negative 4 times, negative 1 times 4 is negative 4, minus 0, so we're just going to get negative 4. So I'm going to go ahead and hope that you're catching on to this pattern, but what I will show you then is this is going to be what we'll get when we continue calculating those minors. So again, when we're looking at M22, so I got this 4 by just crossing out row 2 and column 2, and 1 times 4 minus 4 times 0 would get us 4, and so on and so forth. Alright, so you're going to have to calculate your minors in that way, and then we're going to need cofactors. We're still on this path of trying to find the determinant of A. And so what we're actually going to end up with is going to be using these minors and then changing the signs of some of them. What you're going to be seeing is the cofactors, we're always going to be taking that first minor and just multiplying it by a regular old positive 1. But then from there you're going to alternate with signs, so this is going to become negative, this one's going to be multiplied by positive 1 again. So this one is going to change what you had here. And so will this one, so will this one, and so will this one. Okay, we always start with the positive and then you're just going to alternate signs from there. Okay, so that's going to change. Up here you can see that this negative 8 had to change to be positive 8 because we multiplied by negative 1. This one also changed, so sorry, this is going to be a little confusing now. That one didn't change because we just multiplied it by positive 1. But this one we had to change the sign, this one we had to change the sign, and this one we had to change the sign. Okay, so now the cofactors, that's how we're going to get those. Just change the appropriate signs that you need, always starting with positive, and then the alternating ones are going to be changing. So finally we can determine the determinant of A by this definition right here. And you can see what we're going to be doing is taking a mixture of entries from our original matrix times the corresponding cofactors. So this one, A11, would be taking this guy right here times this guy right here, our cofactor right here. So we're going to be taking 1 times 38 plus, and then we're going to go all the way through until there's no more columns. So we're going to have negative 1 times, because this is a 1 comma 2, and we're going to look for cofactor 1 comma 2 times 8 plus, and then we're going to have 0 times negative 26. So when we simplify that, we are going to get 38 plus negative 8, so we're going to get 30. Okay, there is our determinant of matrix A. That is the process. I will say though that you could actually choose any row, not just row 1. So if you chose to just look at this row right here, and then we would have to line it up with this row right here, what you'll see, and I'll go ahead and do that, we have 3 times 4 plus 2 times 4 plus 5 times 2. You're going to get yourself 12, 8, 10. You'll also get 30. So it doesn't matter which row. Sometimes it's a little bit strategic on what one seemed the most easy to work with, but you're going to be able to pick whichever ones you want. Alright, so that is how you find the determinant of a 3 by 3. There's your practice. Good luck.